Hello everyone. In this lecture, I'm going to discuss the basics of artificial neural networks. Deep learning algorithms are a subset of artificial neural networks. As the title suggests, the artificial neural networks are based on working of actual biological neuron. So, I'm going to start off this lecture by discussing how a biological neuron works, and from there, I'm going to take you to how we can mimic the working of the biological neuron and different components of an artificial neural network. And the following lecture is going to be how deep learning networks differ from traditional artificial neural networks. So be sure to watch it. It's a really important and interesting lecture. So first, let's see how artificial neural networks work and what are the different components of it. Okay. This is the biological model of a neuron. So I'm going to restrict myself with two major parts of a biological neuron, namely the dendrites and axon. The biological neuron accepts incoming signals from other neurons through dendrites, and the major function of a neuron is to calculate the weighted sum of these inputs, and depending on whether the sum is exceeding a particular threshold value or not, it fires an output signal to other neurons via this axon. The equivalent model for this is depicted through this particular model, Michelowitz and Pitts model. So this calculates a weighted sum of all the inputs and calculates the sum. If the particular sum exceeds the threshold, output signal is fired. We just saw a very first artificial neural network model. The model calculated the weighted sum of inputs and calculated the output state based on whether the sum crossed the threshold value or not. This particular function is called an activation function. This activation function, which you just saw, is the very basic activation function. So let's look into different types of activation functions that are currently used. As I mentioned before, the activation function sums all the inputs as a weighted input and calculates the output of the neuron. The three most commonly used activation functions are sigmoid, tan hyperbolic, and ReLU function. These two functions are widely used in conventional neural networks, and rectified linear unit is widely used in deep learning applications. The sigmoidal function is nothing but 1 divided by 1 plus exponential of negative x, so where x is our input. So this is a plot of a sigmoidal function. It's like an inverted S, and it's continuous, it's differentiable, and the output values lie from 0 to 1. And when the input value is say more than less than minus 30, the value is approximately equal to 0. So as we go towards negative infinity, the value is approximately 0, and as we go towards plus infinity, or say like above 30, plus 30, the output of the sigmoid function is approximately 1. So moving on, tan hyperbolic function. This is the plot of a tan hyperbolic function. It's really a nice S shape with a slanted S shape. Again, both differentiable and continuous throughout. The key difference is the value of the slope between these two and the output range. So tan hyperbolic is between -1 to +1, and again when we go below the value towards minus infinity, it is really close to -1, and when we go to plus infinity, the value is almost equal to 1. Moving on, this is ReLU function. ReLU stands for rectified linear unit function. So this is a piecewise linear function, but overall it's a nonlinear function. It's not differentiable at 0. and because it's linear, it's very easy to calculate the differentiation in between these regions, but for 0. And the advantage of ReLU unit is the output is linearly dependent on the input. So here it's nothing but maximum of the input and 0. So here 0 is maximum, and once we cross 0, it's basically the input itself. So the advantage is the output of ReLU unit can go well beyond 1.0, and it basically depends on the input value. So comparing all these three, so the red one is the ReLU, blue one is the sigmoid, and the green one is tan hyperbolic. So for tan hyperbolic, the function, the output is between -1 and 1, and it's continuous and differentiable everywhere. With the sigmoidal function, it's again continuous and differentiable, but the output values is between 0 and 1. The slope changes for both these values continuously, but the slope for the tan hyperbolic is more than the slope for sigmoidal function, a point to be noted. And for ReLU, it's piecewise linear, and the output of the ReLU is different for different values. There is no fixed range, but the lower limit is 0, and it's piecewise linear. So it means it's not differentiable at 0. These three are the major activation functions used in neural networks. The first two are used majorly in neural networks, and in case of deep learning, ReLU is widely used. The reason behind this is, in case of tan hyperbolic and sigmoidal, they have two major drawbacks. One is the differentiation becomes tedious. So in case of deep learning algorithms, we have a lot of connections, and it's more than 1 million connections, and because of this, calculating the derivative for tan hyperbolic and sigmoidal and for 1 million parameters, it's really difficult. On the other hand, since ReLU is piecewise linear, it's very simple and very quick to calculate derivatives. So ReLU is used in place of these two. And one more thing, in case of tan hyperbolic and sigmoidal, the network fails to learn beyond a certain point of input values, because these two either saturate between 0 or 1 or plus minus 1. So when the input values are large, so there's no learning by the network. So it's a very big negative aspect of these two. So ReLU comes into rescue, and as I told before, ReLU is widely used in deep learning community. The three activation functions which I just described are nonlinear in nature. Now, the $1 million question: why do we need a nonlinear activation function? Can we just solve our problems using linear activation problems? The answer is yes and no, and mostly no. The reason is because our data is not linearly separable. Let's take for example a classification problem for AND, XOR, and NOT. So in case of AND and NOT, the data is linearly separable, but in case of XOR, the data is not linearly separable. We need powerful nonlinear activations to do the classification problem. Now, the next question is, how do nonlinear activation functions help us to classify nonlinear data? To answer this question, I'm going to give you an analogy. Let's say a scientist is performing a biochemical chain reaction in Earth, At Earth, we have a problem of gravity, and every time the experiment fails. So, our scientist is sending his sample to International Space Station to perform his experiments where the effects of gravity are negated. So, uh, what he does is just transfers his sample data, a sample of the experiment, to a different space, literally space, where the effects of gravity are negated, or whatever the problem which caused him not to do the experiments in Earth are negated, and the experiment is done, and the result is acquired. Similarly, what these nonlinear activation functions do is take input data and transfer the input data into a different space. The term is hyperspace here. So the nonlinear activation function take a input data and transfer the input data into the hyperspace. In the hyperspace, all these data are linearly separable. So essentially, what this nonlinear functions are doing is transferring this to a hyperspace, and where they are linearly separable, now we have a linear classifier, and the data can be classified easily. So this is how nonlinear functions does the job. In order to better do this, there's a very nice blog post by Christopher Ola. In Christopher Ola's blog, there's a nice blog post about this topic. For example, like how an input data which is not linearly separable can be separated by transforming this input data into a hyperplane and classifying them linearly. So this is a really nice blog post, and I would highly recommend you all to go through it. I'm posting the link in the description. So this is all about activation functions. Now that we have an output, we need to measure the performance of our network. That is, calculate the loss of our network. And in order to do so, there are some standard loss functions for each and every problem. So here I'm going to discuss two loss functions, one for regression problem and one for classification problem. The two major loss functions or error functions are the mean square law error and the cross entropy loss. And mean square error is mainly used for regression problems where the output is an actual number, and cross entropy is more useful for classification problem where the output is one particular class and we try to calculate the maximum likelihood of that particular class. The mean square error is the sum of the Euclidean distances of the difference between the predicted output and the actual output. So here yi is the predicted output and yi hat is the actual output. So I'm calculating the difference between the predicted and the actual outputs and summing it over all the examples. Pictorially, it looks like this. So let's say the black color denotes the actual output of that particular example, and the blue is the predicted output. So we are calculating the distance between the predicted and the output. So the red line denotes the Euclidean distance between these 2 points, and it is summed over all the different examples. And what we are trying to do in machine learning is in neural networks in general. So we are trying to minimize this particular loss, that is minimize this particular distance, so our predicted and the actual outputs are very close to each other. In case of classification problems, the output is actually a class number, so our mean square loss won't be of any use to us. So in these problems, we try to use a different loss function called the cross entropy loss. So here we try to find the maximum likelihood of the predicted class to that of the output class. So in general, in case of optimization, we try to first calculate the loss and then minimize the loss function. But in cross entropy, we try to increase the maximum likelihood with the loss. So the trick here is that the maximum of a function is equivalent to the minimum of the negative of the function. So in other words, so this is the maximum likelihood of the predicted class to that of the output class. So in order to increase this, we can equivalently multiply negative sign with this particular function and find the minimum. So which is the standard procedure, and which is the loss for the cross entropy loss. Now that we have calculated our activation function and calculated our loss, it's time to go and minimize our loss and find the global minimum. The standard operating procedure is through finding the gradient and follow the gradient towards the global minimum. So let's assume that the loss function follows this particular pattern. Here I have plotted the loss with one of the model parameters. So this is a global minimum. So once I initialize my model parameters, after my first iteration, I'm going to end up in one of these points. The task of the algorithm is to minimize the loss and march towards global minimum. So I'm going to start off, say, with this particular point over here. So at each and every iteration, I'll calculate my gradient, that is the slope, and march towards this point. So this is how optimizers work. So there are different types of algorithms based on gradient descent, like stochastic gradient descent, RMS prop, ADAM, etc. I'll be discussing all these algorithms individually in later sessions. So for now, let's move on. The capacity of a model is denoted by the number of model parameters you include in your model algorithm, and as you fit, there would be three different cases: underfit, overfit, and optimal capacity. To explain this, I'm going to take the example of polynomial regression. I'm going to use quadratic data and try to fit polynomials of the order 1, 2, and 10. So let's see what happens. So as I told before, my data is quadratic in nature, and this is what happens when I try to fit a linear function to a quadratic function. So this is my predicted and this is the actual fit. Clearly the model is underfitting category, and I need to increase the number of model parameters to match the predicted output to that of the output actual output. So I'm going to increase the number of model parameters to 2, which is actually required, and so you can see clearly the difference between these two. The predicted output and the actual output are really close to each other. Okay, the final case is overfitting. So I'm going to increase the number of model parameters to 10. So this is what happens when I try to overfit my model to the data. So you can see the as we increase the number of parameters, it shows a very weird behavior, and it doesn't match with the actual output, the predicted and actual output. In case of neural networks or any machine learning algorithms in general, the problem is you won't know the actual data distribution, or what is the ideal optimal capacity of your model. So you need to have some hit and trial basis to calculate the optimal capacity. For example, in my case, I knew that the model was quadratic in nature. So let's say I don't know how my data is distributed, or like let's say I don't know the capacity of the model. So I start with one and then proceed to 4 or 5 parameters and see which is the most accurate fit in order to find the optimal capacity of the model. We now have learned different aspects and components of a neural network model. So let's talk about a dataset. We split our dataset into three different types: training, testing, and validation. Training data consists of the majority of the portion of our dataset, generally around 60 to 70%, or sometimes even slightly more, depending on the volume of the data you're having. And you use the training dataset to train the model and calculate the error for, and you use part of the data set for testing, let's say around 20% of the data set. So you try to calculate the loss, and once you calculate the loss in the testing data set, you adjust the model parameters in the training, and you again test it in the data set and try to minimize the testing error. Once you're done these two, you create a validation data set with the remaining data set to test the model in new examples. You might ask, why do we need another validation dataset when we have testing dataset? The problem is you're using testing dataset to adjust the model parameters and train it again. So in order to test a model in a real world example, that is unseen examples, so we need a validation dataset. After we split our dataset into three and run a few epochs, we are going to run into another case of underfitting and overfitting. This is quite similar to the ones which I described before, but the one which I described before is entirely on the training set. So now we have a test set also. So let's see how underfitting and overfitting problem troubles us. Underfitting is the case when the training error is large. So this is almost same as that I have described before. Uh, and in case of overfitting, the difference between the training error and the test error will be high. So this is in the case when our model algorithm performs really well on training data set and performs poorly on unseen examples in the test set. Another important component of a model is called regularization. These regularization techniques aim to reduce test or the generalization error and not on the training error. These strategies are really important because they improve a model in performing in real world examples, unseen examples. Some of the examples include dropout and early stopping. We'll discuss these algorithms, these strategies in detail later. So this is all about the basic of neural networks. Of course, there are lots to discuss about neural networks, but this much is enough for you to understand deep learning algorithms. So as I told before, deep learning algorithms are basically a subset of neural networks. So in the following lecture, I'm going to discuss what are the key features of deep learning model and how they differentiate from the conventional neural networks. So it's going to be a very interesting lecture. So I'm looking forward to it, and hope you guys have learned something new today. Thank you.